So this one here, find algebraically the value of x for which this quadratic function is decreasing. So I think it looks like this, you know, because it's positive x squared, it's quadratic. And the function is decreasing here and is increasing here, isn't it?
Yeah.
Now, one thing that you need to know is that when you have the original function and the derivative and the second derivative, when the function, its original function is positive or 0 or negative, that has absolutely no effect on the derivative.
Yeah.
Okay? But when the function is increasing or flat or decreasing, then the gradient is positive, 0, negative. And the first derivative being positive, 0, negative has no effect on the second derivative. But when the first derivative is increasing, flat, decreasing, then this will be positive, 0, negative. Understand?
Yeah.
So when you just, let me just go through this with this cubic function here. So this is the original function. Let's suppose like that. And you see how that's negative here, positive here, negative here, and then positive here? That has nothing to do with the first derivative.
Yeah.
Now we can mark these points so they see how that's increasing. That function, the function is increasing.
Yeah. And that's where the derivative will be positive.
That's right. And you look at that point there, and that point there, that's when you have that and that, right?
Yeah.
It's flat, so the gradient is, so the stationary point, so the first derivative is 0. And when you have between that and that, the function is decreasing, so you have that and that, right? And also here you get this. Now let's have a look at the first derivative increasing, okay? Let's do that with orange color. So first derivative, so gradient is increasing from here onward.
Yeah.
You see that? Because the gradient is negative, but then become less negative, less negative, less negative, and 0, and then positive, even more positive, even greater positive, right?
Yeah.
So from that point onward, so I'm going to actually copy this thing. So you have this. Maybe it's just the profile of this. Like so. We see that using the orange color, that bit is where the first derivative is increasing. And that's where the double derivative is positive. That's why if the double derivative is positive, we say it's concave up. And that's why we say we have minimum. So how do you know whether a stationary point is maximum or minimum? If the second derivative is positive, then you have minimum. Now over here is when the, see the gradient is really positive, less positive, less positive, less positive, and then 0, and then negative, even more negative, even greater negative, right? So the first derivative is decreasing, so the second derivative is negative, okay?
Yeah.
Now, and over here, you can see that if the second derivative is negative, then you have concave up, like this shape here, okay? And therefore, you have maximum. There's a maximum there. And obviously, what color do I have left? That one there is inflection point. So if the second derivative is 0, that's the meeting point of the concave down and concave up. So I think you already know these stuff.
Yeah. So
algebraically, so just take the differentiation. That's equal to -2 plus 2x. And just have to, because it's decreasing, if the function is, look at this one. If the function is decreasing, then the gradient function is negative. So just let that negative, that's less than 0. And you have 2x is less than 2, just plus 2 both sides, and x is equal to less than 1. That means whatever this function is, it's a parabola. and that value is 1.
So wherever x is
x is
less than
less than 1 over here, then you have the function decreasing.
I see.
Yeah, and what about this one here? Well, it's a cubic function. It's like that, okay? Well, just have to let the derivative equals to 0, you know?
0.
That's negative 2x, 6x squared, let that equal 0. So 6x squared negative 2x equals 0. So factorize with 2x, then you get 3x minus 1 equals 0, right? So you have 2 stationary points, which is x equals 0, and then 1 on 3. Do you follow everything?
Yeah, that one's fine.
So they're just wondering about the stationary points. So that's 0 and 1 and 3. So which one is max and which one's minimum?
You have to find out.
Well, there are two ways of figuring out. If you just know the orientation, whether it's like that or like that, you see how that's a positive 2x cubed, right?
Yeah.
That means maximum will occur first and then minimum.
Okay.
Like that shape. So and then of course this is 0 and this is 1 on 3. So that's minimum, that's maximum. If it's the other way around, then 0 will be the minimum and the 1 on 3 will be the maximum. So that's what we're figuring out.
I think they expect us to find the nature of the stationary points using
sine table.
Yeah, probably.
So you do something like, you know, x here, and
then y dash
0, and then this is y dash, and 0 a little bit, you know, 0.1, negative 0.1, and this is 0 here, and negative here, positive here. That means it's like that, you know.
Yeah, I find it very time consuming to do.
That's very time consuming. That's right. And you do it for x, and then there's another point, 1 on 3, 0.333. So just go for like maybe 0.4 and 0.3, and then this will be 0, negative, positive. This is the y dash, negative, 0, positive. So that's minimum.
Yeah.
So you do something like that for that and that. So a third method, of course, is the double derivative.
Yeah, I think that's the way they're expecting us to. No.
Yeah.
They're asking us to use a double derivative as well.
So if you take the double derivative here, that's negative 2 plus 12x, right? Differentiation of that.
Yeah.
And just plug in the points 0. Then you get negative 2, right? Therefore maximum. Plug in 1 on 3 there, then it's negative 2 plus 12 times 1 on 3, which is negative 2 plus 4, which is 2, which is greater than 0, so therefore minimum.
Yeah, which obviously is much more efficient.
Yeah, which if it's positive, then minimum. If it's negative, then maximum, okay? As shown here, okay? So that was rather pretty straightforward question. All right.